Hello everyone, welcome to this tutorial on reflection. We are going to cover a Leavenworth question about convex and concave mirrors, and we're going to make mention to plane mirrors as well. And hopefully I can help you be able to solve any type of reflection question that you may encounter in the exam. So even though we're gonna look into how to solve this question, we might go into how to solve any other potential questions or variations of this question that may appear. So first of all, we are asked in this question, what is reflection, right? So if, let me change this to a more suitable let's say 50. Okay, so yeah, 60. So what is reflection, right? So when you see yourself in a mirror, what do you see? What do you see? So what is reflection? So when you see yourself in a mirror, what is actually happening? Well, if you've seen the tutorial slides, the lecture slides, you may have seen that if you're, let's paint here, let's say that you're going to be here in front of a plane mirror, right? So let's say this is a plane mirror, okay, and you are going to be, let's say, here, right? That's you. What's happening here is that photons of light are actually traveling from your face, right? They're traveling in a straight line. They hit the mirror, okay, and then they're gonna bounce back. They're gonna bounce back in the same direction, right? Just like if you get a tennis ball and you throw it against the wall, it's gonna go back towards you, right? Until it meets your eyes, and then the photon of light will have recorded that image in a way, right? It will have recorded some information, which will be the light that has left your face, and will go back to your eye, and therefore you'll see your eye, or you see your nose, or anything like that, right? So if you want to look at your feet, right, light that goes from your feet will go all the way, hit the mirror, okay, and then bounce and meet your eye. Okay, so only the light that bounces in a certain point in the mirror and meets your eye at that angle will be the light that comes from your feet, right? So if the light comes in this way, and it won't reach your eye, and if the light goes a bit higher, it won't reach your eye, as it will go that way, right? So just by looking at the same path, you will see the light that comes from your feet. So therefore, what is reflection? Well, if we can think of this as a ball bouncing on a wall, we can see that light is just reflecting, right? So it's just bouncing. So it's the bouncing of light. Okay, it's the bouncing of light of a surface. Right? So light bounces off a surface and therefore reflects. Okay? So you can also encounter that not all light reflects. So these photons of light, let's say 100 photons of light hit the mirror, some of them will be absorbed by the mirror, right? So in this case, light will not be reflected, will be absorbed by the mirror. Believe it or not, some light may also be transmitted, right? So usually a mirror is really effective at reflecting light. So you could say that 99% of the light is reflected, 1% might, 0.9% will be absorbed, and 0.1% will be transmitted, or even smaller than that, right? On a glass, for example, a simple window, if you look through a window, you'll see that about maybe 80% of the light is transmitted. But if you look in the mirror, you can actually sometimes see reflections in the mirror, right? Especially if you're in the car and you can see reflections in the mirror. So a window can reflect light, even though we think it's completely transparent. And again, some bits of that light will also be absorbed by the mirror, by the window, right? So every single object, in a way, reflects an amount of light, absorbs an amount of light, or transmits an amount of a certain amount of light. Okay, so the next part of the question says, draw a ray diagram to show the formation of an image in a convex mirror. Right, so first of all, what is a convex mirror? Well, as you may know already, let me see if I can, yeah. As you may know already, there are two kinds of spherical mirrors. Okay, and these these two types of mirrors just come from a sphere, right? So we call them spherical mirrors because they're like the cross section of a sphere. So let me show you how is this even possible. Okay, so let me see if I can get this to 1 pixel. Okay, so if you had a sphere, okay, it would look something like this, right? That's the front of the sphere, and that's the back of the sphere. Now, what happens if you cut a sphere? If you cut a sphere, make a cut anywhere, you'll get something that looks like this, right? This is the outside, and then there, right? So you could look at here, if you see yourself in, right, you see this looks like a cave. So if it looks like that, it looks like a cave, we call it a concave. Right? So if you have the inside of a cave like mirror, then we call that a concave mirror. Right? Now that's easy to remember because it says cave. Now, you could also be looking at yourself from the outside of the mirror, right? So in this case, instead of having that mirror, you're gonna have the outside of the mirror, right? So it's gonna look like this, and you're gonna look inside. Sorry, you're gonna look from outside, right? Now we call these convex mirrors. Convex mirrors. And there's no more types of spherical mirrors, and therefore it's easy to remember because this one says cave and this one doesn't say cave, and that's it. So if it doesn't say cave, it's the other one, aka convex mirror. Okay, so now how can we work with this? All right, well, as you may know, first of all, before we get into the actual question, as you may know, I'd like to realize what's happening in a mirror. So as we said earlier, here's a point of light, right? Could be your nose or whatever. Goes straight. Let me try to make this as straight as possible, and hits the mirror. Okay. Now, what happens if what happens if it comes at an angle? Well, if it comes at an angle, it would go that way, right, and hit this part of the mirror, right? And the lights, the law number 1 will tell you that if it hits the mirror, and this is the normal to the mirror, aka also known as the tangent to that point in this mirror, the light bouncing will bounce at the same angle, right? So this is one angle, let's call it alpha, or is the angle of incidence, right? Alpha I. Then this will be the alpha reflected, which will be the same. Okay. Now, to your eyes, let's say here's is your eye. To your eye, your brain will think that the light it's actually coming straight, right? So if you have a point of light coming from here, the light will bounce here and come back straight, right? But to your brains, it will not think that it's coming back and forth and coming back for it. It will think it's just coming from here, right? So your brain will think it's doing this whole path, when in reality what's happening is the photon of light is just going here and back and forth. All right, so now how can we use this? Well, if you have light coming from, let's say, here, right? Coming here, and your eye is here, right? Light coming from this point, right, will coming from here, whoops, will coming from here, bounce and come back in here, right? What's happening here is your brain, again, will think it comes from this point. It doesn't think it's bouncing. It just thinks it's coming from this point. And then the light that comes in from here, and again, bounces back out at the same angle. You'll see back in your eye, it thinks it comes from this point, right? And light that comes in from here, I'm going to make these lines actually full lines. So light that comes from here will think it comes in that way, and will also think that it comes in from that point, right? So as you can see, these lines kind of like diverge, which means they get separated, but your eye thinks they come all from this point, which is where they all converge, right? So the image will be formed here, and we call this image virtual, right? Why? Well, it's virtual because the light, it's actually going that way, but the light, we think it converges in this point. So the light is converging opposite to the direction of the light, right? And we call that image virtual. You could also argue that it's converging at the like the apparent crossing of the light rays. Okay, now the rules are two, really, and it really is just one. So rule number one is that the light hits the mirror and bounces off. Incident light and reflected light bounce with the same angle. So what we were talking here, what we're talking here, right? So light bounces at the same angle, right? So this would be as incidence. Let me correct that. As incidence. Okay, so what this means is, again, just think of a pool table. The ball will hit the wall and will come out at the same angle as it was going to hit the table. And the law number two will be that this happens in the same plane. So it all happens in the same plane, right? So if you're playing pool in this table, right, and you've got a ball and you hit it this way, you think it's going to go that way, right? Unless you hit it really hard, but not, for the sake of this argument, the ball is not going to get out of the table, right? It's going to stay in the same plane as the table. All right, so how can we apply this to spherical mirrors? All right, So we're being asked to solve, says spherical mirrors. Oops. Oh wait. Spherical mirrors can be convex or concave. Draw a ray diagram to show the formation of an image in a convex mirror. Okay, well in that case, let me see if I can find. I've prepared here a convex mirror. I'm going to bring here. Oops, a bit too big. I'm going to put in this convex mirror somewhere here. Okay, so how does light converge on a convex mirror? So zoom in. There we go. Right, so let's imagine that you are here standing on a convex mirror. Right, and we're going to use this point to illustrate this picture, right? So light that goes out of your head, you should always look into these three scenarios, because otherwise it's going to make things a bit too difficult. Well, I can use this line tool. Light will travel straight and hit the mirror, right? Now what happens when light hits the mirror? Well, a photon of light that hits this mirror, it will think that it's a very, 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 very small plane mirror, right? So whatever light that is coming out at this point, right? Let's say call it a tangent, right? At this point, oops, I'm going to draw a tangent in blue, right? So this point, at this point here, it's done in black for some reason. There, right? So if you have a tangent here, right? The normal to this tangent will be perpendicular, right? And so the light will actually bounce again at the same angle of incidence. It will bounce that way, okay? So what's happening here is your light ray will think that is coming from this point, right? So it will think, oops, it will think that it's coming from that point. Now, what's happening here? This point here, we call it the focal point, right? The reason is because if we had all the lights coming parallel, right, light coming from this way, we'll also focus on that point, and all the light coming parallel will focus on this point, right? If it was a convex mirror, all the light comes parallel will, if it was a concave mirror, all the light that comes parallel will focus to this point, which happens to be halfway between the center of curvature, right? So the center of curvature will be here, right? And that would be like the radius of this mirror. And so halfway would be here, and we call this F, right? So now let's say that you pick another light ray. Let's say that it's going all the way, you think it's going to the center of curvature, right? Well, at this point, you know that light, the tangent here, it's going to be the same. It's going to be perpendicular to this light ray. So the light that comes in goes out as well. All right, and so these two are going to cross in this point. Okay, now let's pick another case in which light is supposedly going to the focal point, right? So it will bounce somewhere, bounce around here, and your brain will think that it's going all the way, oops, sorry, and your brain will think it's coming all the way straight, right? Because it, as we said, it's going to go parallel, right? So if it goes parallel, it will go through the focal point. If it goes to the focal, in the direction of the focal point, it will bounce out parallel. What's happening here is your eyes will think that the light is actually coming parallel, right? And I didn't really do this off. Let me see if I can get this a better. If this was made to scale, you'll see that the light is actually, so it would be somewhere along these lines. Whoops. It will be somewhere like here, and then it bounces out that way, and so it will appear that it's going this way. And look at this, all the light meets here, and this is the point where the image is formed. And so this is the point where the image is formed. In here. Right? So what's happening here is that if I am this size, all right, so I pick this again. If I am this size, I'm going to see myself here smaller. What does this mean? Well, this means that I was this size, about this big, and now I'm about this big. So we call this that the image, let me use, no. Okay, the image has been diminished, right? So if I type here, the image is diminished, so, okay, actually, let's do better. What are the options? So the image can be diminished, or magnified. It could be real or virtual. And it could be upright or inverted. Okay, so let's say now the image, what is it? Is it real, or is it or is it diminished, or is it magnified? Well, clearly the image is much smaller, right? So it's obviously diminished. The image is real because the light rays, sorry, the image is virtual. I should have probably drawn these, because these light rays are going this way, right? They're going first in and then out, then in and then they go out, right? And so the light is not actually crossing at the image, right? This is just apparent. We just think it's crossing there, but it's actually going that way, it's actually going that way, and this way, and all over the place, right? So the image is virtual here. And so, and it's pretty easy to see that the image is, so the image is going up the same way we are standing up, right? So it's in the same orientation, and therefore the image is upright. Okay, so we can say that in this case, the image is diminished, virtual, and upright. And as it is, and you can believe me, or you can try this yourself, this is always this case for convex mirrors. Always this case for convex mirrors. So no matter how far you're from the mirror, you will always see yourself smaller and you will always see yourself in a virtual image. Now, what's also good is that you will always see yourself in an upright, meaning in the same orientation as you are standing, which is really, really useful. For example, if you are in traffic and you see one of these mirrors that are convex for like seeing on on a bend or an area with poor visibility, it would be very inconvenient if the car you're looking at from the distance all of a sudden flips. And it would be really, 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 really annoying if the car is coming to you upside down. So the good thing is that the image is always upright, meaning in the same orientation as it should be, which is a bit like plane mirrors. You don't all of a sudden like think of of the image as flipping. Now, this is not the case for convex mirrors. For concave mirrors, concave mirrors, depending on where you're standing, you will be upright or you will be inverted. So if you've ever taken a spoon, look at the inside of a spoon, you'll see that the closer it is to your eye, you will see the image to be normal, just like a mirror. And as soon as you move the spoon out, there'll be a point, which is the focal point. You'll see yourself like you don't really see yourself. It'll look all like a blurry mess. And then you just move it outside, and then you'll see upside down on the spoon, right? And so this is why we don't use convex mirrors, concave mirrors for traffic, because again, it would be very, very inconvenient if my car all of a sudden flips upside down. Okay. The next question says, a person looks at her image in a shiny spherical decoration when her face is 30 centimeters from the surface of the decoration. The diameter of the decoration is 20 centimeters. Find the position of the image. Okay, well, this one I'm going to write it here. And the reason I'm going to do it here on the side is because I want to extract all the information from this question. Right, and and I'm actually going to add a couple questions to this, because that I'll add after solving this part of the question, because it could easily come up in an exam. So it says a person looks at her image in a shiny spherical decoration, right? So it's a shiny spherical decoration, it's going to look like that, and you could assume that you're just looking at, let's say, this part of the decoration, right? So you should always kind of draw a picture just to make yourself comfortable with what it is that the question is talking. So in this one, it's true, we have an image, they've drawn a picture here, for example, but it doesn't always is the case, and the picture not always gives you all the detail, and it also helps your head grab a good idea of what's going on. Plus, you kind of receive the information much slowly than just remembering all by heart. So we're going to write down all the information. We're going to draw pictures of what's going on. So we say you have a spherical decoration just like this one, and you could assume that you're just looking yourself in like half the ball. So you're really looking here at a convex mirror, right? So it was the very first example I said, it's if you look at the outside of a sphere, you'll be looking yourself into this ball from the outside. So it's going to look like a convex mirror. Okay, now what's the next part of the next good bit of information that they're giving us? So a person looks at her image in a shiny spherical decoration when her face is 30 centimeters from the surface of the decoration. So this seems like a good piece of information. Now, I wouldn't recommend to write all of this, because that would be a waste of time. But what you can do is you can just write very, very shortly something that will easily give you access to this information. So here it says, a person looks at an image in a shiny spherical decoration. That's not really that useful. It basically just tells you convex mirror when her face is 30 centimeters. Now, her face is 30 centimeters. What's her face? Well, her face will be the object, right? So we have the object or the image. Well, her face will be the object. And we write u for the distance of the object to the mirror, right? So, and it says u is equal to 30 centimeters, right? So you just write u equals 30 centimeters, and that's it. I don't have to write face from the woman to the object, right? You don't have to write here an essay. This is more mathematical than anything else, right? So u equals 30 centimeters, next thing. Now, the next thing piece of information tells you is the diameter of the decoration is 20 centimeters, right? So the diameter of the decoration is equal to 20 centimeters. Now, what did we say earlier? Now, a spherical mirror has a center of curvature, which is basically like the center of where the compass is, right? And that's the radius, essentially, right? That's the radius. And look at that. So if the diameter is 20 centimeters, the radius is half of that. And that would be only 10 centimeters, right? Cannot be easier. And now another thing I said earlier is that your focal point, F, will be midway between the radius and the mirror, right? So your focal point is literally half the radius. So it will be 5 centimeters, meaning that the focal length is 5 centimeters. All right, so now how are we going to solve this? Okay, well, if you've looked at your physics book, it will give you a few formulas, one being 1 over F equals 1 over U plus 1 over 5. Over V. 5 over V, right? And so what this means is F is the distance, is the focal length, U is the distance of the object to the mirror, and V is the distance from the image to the mirror. Now, if you're looking at your textbook, this will tell you is a concave mirror version. That's not entirely true. This works for everything. You just have to define what is the sign convention of each of these signs, right? So the sign convention is really easy. If the object is in the size of where the light is coming, for example, if this is the mirror and it's convex, everything, not even that, if the object, let's say, is a sphere, if the object is inside the sphere, it's negative. If the object is outside the sphere, it's positive. And that's the sign convention we've picked, and it works fine, so stick to it, don't change it. Okay, so for a convex mirror, what happens? The focal point is inside. So focal point is negative for a convex mirror, right? Then it will be positive for a concave mirror, right? Because it will be okay, so what's happened? I'm gonna cut this. Okay, so in order to solve this formula, we're gonna try to we need to first establish what are the convention, the sign convention of this formula, right? So F stands for the focal length, right? So as a rule, we're gonna be using this rule. So if, as a rule, we're gonna be using that anything in the real world, right? So let's say this is the back of the mirror, right? Anything here is positive, anything here is negative, right? Anything that is in front of the mirror is positive, anything that is behind the mirror is negative, right? So what happens in a concave mirror? So in a concave mirror, right, you're looking yourself here, as to show that this is the back. In a concave mirror, you've got a positive focal length, right? Because your focal length will be somewhere here. You will have a positive U, right? And then your image could be either here or here, right? So you don't really have to look into that. Maybe they tell you in the question, oh, the image is virtual. So it will be positive if real and negative if virtual, right? Now on a concave, on a convex mirror, you'll see that on a convex mirror, you will see that the focal point is actually behind the mirror, right? So because it's behind the mirror, it's always going to be negative. So it's going to be a negative focal point, focal length. It's going to be a positive U, right? Because, right, how could you on Earth have an object behind a mirror? I mean, you could, but it wouldn't reflect anymore. So the U is always going to be positive. And as we said earlier, the image is always going to be virtual. And because it's virtual, then it's going to be negative, right? So you don't really have to remember this. Just remember that F is always negative for a convex mirror. F is always positive for a concave mirror, right? So F is negative for a convex mirror. F is positive for a convex mirror. U is always positive, and then if the image is real, it's positive. If the image is virtual, it's negative. Simple as that, right? So in this case, we said the image is formed in a spherical mirror that we've said that it's going to be just like a convex mirror, right? So F will be negative. Right? We say U, it's always going to be positive. U. And V, well, we just don't know. Right? Well, I mean, we know because we know it's going to be negative, but if you put in this to be negative, then the answer for V will be positive. Or if you just leave it like that, you'll see that V will become negative, right? Let's do just that, right? So I'm going to bring this 1 divided by U to the other side. So it will be minus 1 divided by U minus 1 divided by F, right? Now this minus, I'm going to put it here. I'm going to put it here, the minus of the F here, this minus here. I'm going to put it here. And so minus 1 divided by U divided by minus 1 divided by F is equal to 1 divided by V. Now, what's going to happen here? Well, I'm going to remove this from here. Gosh, I don't know what this comes from. Oh, forget about it. So what's happening here? Well, I'm going to combine this thing into a single fraction. To do that, I need to make the U, the bottom of the first fraction, the bottom of the second fraction, to have the same things, literally. So what I'm going to do is I'm going to multiply by F in the first fraction, top and bottom. I'm going to multiply by U, the top and the bottom. So I'm going to have something like minus F divided by UF minus U divided by FU equals, and then I leave the rest 1 divided by V. And now what I'm going to do now is I'm going to combine this. You see you have minus F minus U divided by FU equals 1 over V. And then I can bring the minus out, so I would have minus F plus u, right? Remember to make it plus u because you've taken this out of the brackets. And then you would have f and u, and then you have 1 divided by v, right? Now, if you've done your algebra right, you can just invert this two, so you'll have v is equal to fu divided by minus f, forget the brackets, plus u, right? And this minus here can't go in the left, so you'll see that your v will always be negative for a convex mirror. So you'll have f u divided by f plus u. Now, so we said your f will be 5, your u will be, I think it was 30, and then in the bottom you'll have 30 plus 5 will be 35. So it's 150 divided by 35. All right? So what v will be minus 150 divided by 35 centimeters from the mirror, right? So if you have a convex mirror, your image will be formed, for example, here, which is at a distance of 150 divided by 35 centimeters in the back of the mirror, right? And you can just work that out in the calculator, and that's it, right? So the minus tells you that it's behind the mirror because it's virtual. Okay, now this brings us to another part that I would like to cover, that it's not a part of this this question, but it says what would be, let's see if this, it would be the magnification, right? Has the image been magnified? Has the image, oh my god, let's see if I can get this. Okay, has the image been magnified? Is it been diminished? Is it bigger? What is it? So so we call this the magnification factor, right? So what this really tells you is that if the image is bigger than 1, it's basically like multiplying this by something, right? So if the magnification factor is equal to 3, then it means that you've multiplied the image it's 3 times bigger than the object, right? So you call it magnified. If you multiply something by 1, you could say that the image is the exact same because it's the same as multiplying by 1. And if you multiply by something smaller than 1, right, say 0.1, you'll see that your image is just like multiplying by 0.1, which is the same as, it will turn it into something smaller. So what is it? Is it going to be bigger than 1 or smaller than 1? Don't worry about the minus signs in this, because it really doesn't tell you anything. You want the absolute value, so the 3, the 1, or something between 0 and 1, right? So, and as it turns out, the formula will tell you that m is equal to v divided by u, right? So if my image is, remember this, if your image is bigger than the object, right? Say your image is 2 and your object is 1, well, there you have it, right? So your image being y, so you could have it 2 ways, right? You could have your object to be, let's call this x, this big, right? And your image here will be this big, right? Y. Then y divided by x, right? So if this image is bigger than this x here, then your image has been magnified. And as it turns out, it also follows that it's v here, u here, not that, and v here to the image object. And this is for image. Okay? So you could either get, they could either give you the height of the object with respect to the height of the image, sorry, the height of the image with respect to the height of the object, or they could give you the distance of the image to the distance of the object. In this case, we have the distance of the image with respect to the distance of the object. We found that the distance of the image is 150 divided by 35, whatever that is, right? So it would be, what, 150 divided by 35 will be about 4 times, right? So it will be that divided by u, and the u we said is where is it? 30 centimeters. Right? 30 centimeters. 30 centimeters. So we're basically saying that we said that 150 divided by 35 is about 4. Let's just say it's 4 divided by 30, meaning that this is way smaller than 1, meaning that the image, it's been diminished. Simple as that. If it's smaller than 1, it's diminished. If it's bigger than 1, it's been magnified. And if it's 1, it's just the same size. Okay? Now, just to finalize the question is asking us, concave mirrors rather than convex mirrors are used by dentists to examine teeth. Explain why. Okay, so now we're no longer looking at a convex mirror, we're looking at a concave mirror. Okay, so I have prepared here the opposite, which is a concave mirror. Oops. Can we get this smaller? Nope. There you know. Nope. Okay. I'm gonna take this. Nope, it doesn't let me. Okay, well, I'll just work it out in here. Now, what's happening here is that let's say that a dentist uses a concave mirror. These are usually the things that they hold in their hand. They look like a bit of a spoon, and these they put. Nope, it doesn't really want to. Let me see if I can open a new page. Make this smaller. Concave mirror. Yeah, this one. Perfect. Okay, so they put these very close to your tooth, right? So we are going to assume that the tooth, it's way closer than the focal length. All right, so let's say that the focal length, that the focal point is somewhere along this lines, right? So that could be the focal point. And so your tooth is going to be there, right? And for all terms and purposes, we're gonna say the light is coming out of this point. Okay, so the focal point is here. And we could say the light that it's coming straight will bounce off this point. And we said the light that's coming straight goes straight back, goes all the way back to the focal point. right? So we'll cross somewhere along those lines. And then light that goes through the center of curvature, the point that hits the axis, will what? What's going to happen to it? Will bounce at the same angle as it is reflecting, right? So notice that this ray, it's going that way, and this ray, it's diverging from it, right? So these two rays are actually diverging. What's happening is it's going to converge behind the mirror. And what happens when it converges behind the mirror? Well, the image is going to be virtual. We know that. It's in the apparent cross-section of rays. So what is happening? What's happening is that light is actually converging in this side of the mirror, which is behind the mirror, is here, right? So the image is going to be behind the mirror. So what's going on here? The image is clearly augmented, right? Look at the size of this. The object is about this size, and the image is about this size, which is way bigger than the object. So the image is definitely augmented. It's upright. And what happened to it? It's formed behind the mirror, so it is virtual. Why is it virtual? So the light is actually going this way. This ray is going that way, yet the image forms behind these light rays, so that's why it is virtual, right? That's really it about mirrors, concave mirrors used for dentists, right? So the idea is that the dentist will use a concave mirror that it's so close to the tooth that the image will look so much bigger that for the dentist it'll be really useful to get a magnification of the actual tooth.